Actors live and breathe in messages, so now we will take a look at how exactly messages are exchanged between them. The most important property of actors is that access to their state is only possible by exchanging messages. There is no way to directly access the current behavior of an actor. Messages can be sent to known addresses, and in akka those are typed as actor_ref. Every actor knows its own address, which is very useful when sending messages to other actors and telling them where to reply to, but it can also be useful to send a message to self. The second possibility is creating an actor which will return the address of the new actor. Most notably, it will only return the address, so the actor_ref, and not the actor instance. It is not possible to call methods on this newly created actor, besides sending messages. The third way is that addresses can be sent between actors within messages. The most prominent example of this is the automatic capturing of the sender in akka. The other important part of how actors work is that they are completely independently executed. Every actor performs its calculations completely locally. They are not shared directly with other actors. The only way to share them is by sending messages. There is no notion of a global synchronization between the steps actors do, because they all run fully concurrently. And message passing is the only way in which they interact. And the way messages are sent is completely one way. When an actor sends a message to another, it continues on its way and is completely oblivious to whether the other actor will receive or process the message. It does not wait for its completion. This means that actors are completely encapsulated and isolated from each other. One could also say that actors are the most encapsulated form of object orientation. We have seen how actors interact as seen from the outside. On the inside, an actor is effectively single-threaded. It will receive its messages, one after the other, and for each it will invoke its behavior, possibly change the behavior for the next message and move on. But it is important to note that processing one message is the atomic unit of execution. Everything an actor does while processing a message cannot be interrupted or interleaved with processing another message. They are strictly sequential. This has the same benefits of making all methods synchronized, as shown in the first part of this lecture, but without the disadvantage of blocking. Blocking is replaced by simply enqueuing messages for later execution. Now let us apply these principles to our well-known bank account example. This bank account will of course be an actor, and it will receive messages. It is good practice to declare all the possible message types expected by the actor and also returned in reply in its companion object. We have therefore here the object bank account, and in that we have case classes. One for depositing some amount. I'm using big integer here to avoid problems with overflow, just because someone might have more than 2 billion Swiss francs in one account. And of course, we need the amount to deposit to be positive. Require is a library function which will simply throw an exception if the condition does not hold. This means that a deposit object which has been instantiated will always have a positive amount in it. The same for withdrawals. We have another case class which gives the amount. And then our actor will have to respond to requests so that we can detect that it actually has performed the work. And for that we have the positive done and the negative failed reply. Now let us look at the actor itself. First, of course, we extend the actor traits, then we import all these message types which we have defined. and the actor starts out with a balance of 0. Then it will handle messages as they are received. We can receive a deposit. In this case, we increase the balance by the amount and reply with a positive acknowledgement. If a withdraw message arrives, we need to check that there is actually sufficient funds in the account. If that is the case, then we deduct the amount from the balance and send back a positive reply. In all other cases, we reply with a failure. This actor is equivalent to the bank account object defined earlier, but including synchronization, because the code in here will be completely serialized. One message entering this behavior cannot interfere with another one, because the other one will be forced to wait its turn in the processing. That is the most convenient feature of actors when working with them. In order to transfer money between these accounts, we need several actors to collaborate. And actors collaborate basically in the same way that humans do. Let me first make a small detour here. Let us say we have an account which we call Alice here. And we have another account which we call Bob. Now we want to transfer money. We could include the code to perform the transfer in the bank account itself, but that would mix up the logic. The bank account should not have to know how exactly a transfer is done. This is why we introduce another actor. Let's call him Tom, who will be our model of the activity to transfer some money. Tom will first send a message to Alice to withdraw the money from Alice, and Alice will eventually reply, hopefully with a success. In case of failure, Tom will just abort the transaction. Then Tom will send to Bob a deposit, and eventually Bob will reply, yes, all is done. And at that point, the transfer has completed, the transaction has been done, and Tom can shut itself down, possibly informing whoever wanted to know about it. How does this look like in code? Well, we need another actor. We call it wire transfer. And this one will also accept some messages. Again, in the companion object, we have the transfer case class. From is a bank account, but we only know the address. To is an address to another bank account. And amount is the amount of money which shall be transferred. This actor also can signal success and failure, and it is good to keep the message set used by one actor local to it and to keep different actors separate from each other. Transferring money proceeds in several steps, as we have seen in the picture. First of all, when we create a wire transfer actor, it will start out with an initial behavior. It accepts only message type transfer, and this transfer tells it from whom to whom how much shall be transferred. So the from actor gets a message to withdraw the amount, and then this actor changes its behavior to await the result of this withdraw activity and basically suspend its execution. It will not consume any CPU resources, it will not run unless a message is actually sent to it. The behavior which we install for the second step, await withdraw, needs to know the account to which the money shall be transferred, which amount that was, and also who sent the transfer command to send back the acknowledgement at the end. The behavior in the second step is defined here. We await the result of the withdraw operation, and a bank account might reply with a done, in which case we proceed. We send a deposit to the recipient account, and then we change behavior to await the result of that operation. If the withdrawal from the originating account actually failed, which means that there were insufficient funds, then we need to tell the client which requested the transfer, and we need to stop this transaction. In the last step, if the withdrawal was successful, we await the bank account done from the account which was supposed to receive the deposit. Once we get it, we confirm that the transaction has been successful to the original client and stop this transaction. Perhaps it is instructive to see this all in action. I have again put the code which was presented so far into an Eclipse project. Here we see the bank account with the well-known messages, and here we have the actor itself, and I've added a debugging feature here. I've said logging receive around the behavior. We will see what that means shortly. It is imported here from the AK event package. Similarly, we have the wire transfer actor, which has also been treated in the same way with logging receives in all behaviors. The last part is an actual main program which runs all of this. Again, this is an actor like in the last example, and we create two accounts, account A and account B, both bank accounts with different names. Then we send to account A a deposit of 100 Swiss francs, for example, and in the initial behavior we await confirmation from this bank account that the deposit has been received. Then we start a transfer of 50 Swiss francs. Transfer is a method which first creates a transaction actor, this wire transfer, called transfer. Then it sends to this transaction the command to transfer from account A to account B the given amount. And then it changes the behavior of this actor to wait for the confirmation. Once it is received, we declare success and stop the program. Again, I have prepared a run configuration for this with the AK main class and as argument the main class, the actor class to be run. I have set here a debug option, AK actor debug receive equals on. This activates all the logging receive blocks so that they tell us when which message is being processed. It is done so at log level debug. Now running it produces a lot of output. Here we can follow the progress of the program. First, the account receives the deposit of 100. Then the application receives the confirmation. Next, we instantiate the transfer and tell it to transfer from account A to account B, amount 50. Account A will then receive the withdrawal message and reply to the transfer with the successful acknowledgement. Then account B will receive the deposit and again reply successfully. At the end, we receive the done message, at which point the application terminates. If we now try to transfer more than is in the account and run again, we will see less output. First, again, we deposit 100 and that was successful. Then the transfer starts. Withdraw 150, which fails. And then we see received unhandled message failed and nothing more happens. This is because in this behavior here, we do not handle this case, and we do not stop the application. So I will quickly insert this case. And when rerunning it, we see again that now it receives the handled message failed and it terminates the application. To recap what we have done, we have modeled accounts as actors, which were Alice and Bob, account A and B in our sample. We have modeled the activity of transferring money from one account to the other as an actor, which was named Tom here. And then we saw how the messages flow to complete the task which is supposed to be done. Actors interact only using messages, as we have seen, but messages can also be viewed like letters. We have seen that actors interact only by sending messages, but sending messages is something which requires one more thought. Whenever you send it, you can never be completely sure that it will be received, as all communication is always a little bit unreliable. The same is true for synchronous method calls, which are also messages in a sense, because, for example, the computer might crash while trying to invoke a method. You could say that then the message was not delivered. If you invoke network transfers, for example, send messages across a TCP/IP connection, then obviously the chances of messages being lost is higher, but nevertheless, you need to always deal with the fact that communication is inherently unreliable. This is something we know from daily life, so we can also employ the protocols which we have developed. Say we have a person here, and this person wants this other person over here to perform a certain task. Let's just say it says something like, please do, whatever it is that shall be done. What we typically do is we do not race past the other person's office and shout in, please do, because then we don't know whether the command was actually heard. What we typically do is we wait for a confirmation. Now the other person, which was listening and was hearing that this person said, please do, might respond, okay. This gives confirmation that the message was actually delivered, and then both can happily go their way. But what happens if, for example, a big noise occurs that shadows this okay phrase, so this person doesn't hear it? Well, we humans are pretty adaptive, so this one will ask, have you heard? And this can go on until the process is complete. We can take this as inspiration for how to construct actor systems which perform tasks reliably, although the communication they employ is unreliable to begin with. Successful delivery of messages requires that eventually we will succeed. In the example with the two persons, it requires that both are perseverant enough to come back to the process and keep talking until the confirmation is conveyed. In more formal terms, delivery of a message requires the eventual availability of a communication channel and of the recipient. We can classify the kind of effort we go to and the resulting delivery guarantees in three ways. The first one is if you just send a message once, then it will either arrive or not. Hence, it will be delivered 0 or 1 times. This is called at most once delivery. If we keep resending a message until we receive an acknowledgement, that means we will resend it until it has been processed, so it will be received at least once, but up to an infinite number of times. because the acknowledgement itself might be lost, and we will keep resending it until that is also successful. If we keep state at the receiver to make sure that only the first received message is processed, then we can ensure that the message is processed exactly once. This is the most costly of the three options. The first option can be done without keeping any state in sender or receiver. The second choice requires that the sender needs to keep the message, to buffer it, in order to be able to resend. And the third choice additionally requires the receiver to keep track of which messages have already been processed. The good thing about messages is that making them explicitly supports reliability quite well. First of all, messages can be persisted. You can take a copy of a message and store it in some persistent storage. You cannot do the same thing with a local method invocation, for example, because that is an ephemeral act. You have one object invoking a method, and the context in which this happens might go away. A message, on the other hand, from one sender to one receiver is something which you can persist. If you include a unique correlation ID in the message, you can enable the exactly once semantics by allowing the recipient to find out whether it has already received this unique message. And finally, delivery can be retired until successful. If the messages were persisted, then retries can even be restarted after a catastrophic failure. For example, if all the computers were down due to a power outage, then once the power comes back up, delivery can restart. But one thing to note, it is not enough to deliver a message to a recipient. If you do not get a reply from that recipient, you can never be sure whether it has processed it. That means that all of these semantics discussed only work if you include a business level acknowledgement. That means that the actor which shall process the message actually needs to say, I have done this specific task. It is not enough for the framework to say, I have put this task into the recipient's mailbox. How do we apply these principles in our bank account transfer example? We can make the wire transfer reliable by logging all its activities to persistent storage so that it has a memory. Then each transfer needs to have a unique ID by which it can be identified in the withdraw message and in the deposit message, so that the bank account actors do not perform withdraw or deposit more than once if resends should be necessary. And for that, they need to store these IDs with their state. The details of how to do this I leave as an exercise for the viewer. The last topic in this section is about message ordering. When you send multiple messages in your system, in which order do the actors process them? An example. Let us say we have an actor Alice, and as usual accompanied by Bob and Charlie. Alice sends a message to Charlie. So far so good. But if at the same message processing turn, Alice also sends a message to Bob, which one gets processed first? You don't know. Conceptually, they are processed completely concurrently. You cannot tell in which order they are processed. Now, if this message to Bob would contain a reference to Charlie, so an actor ref for it, then Bob might, in response to this message, also send a message to Charlie. But since we do not know in which order they are processed, this message from Bob to Charlie might actually arrive before the one from Alice. In the original actor model, those were all the rules. Message ordering is not prescribed by the model. In Akka there is one addition. If Alice sends another message to Charlie, then the order of these two messages will be the same at the receiving side as on the sending side. Either of these messages could be lost, of course, but they will not be delivered out of order. There are other more sophisticated systems, for example the E programming language, where causality goes a bit further. So if Alice sends a message to Charlie, then in Alice's view, Charlie has already processed the message for all intents and purposes. So if it sends Charlie's reference to Bob, then if Bob subsequently sends to Charlie, this should not be able to arrive before the message from Alice. This guarantee is rather expensive to realize, but E has also a different focus than Akka. The philosophy of Akka is to provide the minimum level of guarantees which make the programmer's life easy, but still allow our implementation to be very fast and efficient. Therefore, we chose not to implement the full causality, just the ordering between a single sender and receiver pair. In summary, actors are fully encapsulated independent agents of computation, which run fully isolated from each other, and the only way they interact is by passing messages. Making message passing explicit also exposes the possibility of message loss, but it also allows you to explicitly treat reliability in your programming model. Lastly, the order in which messages are processed is mostly undefined, but we have seen how to deal with that in our wire transfer actor. If you have one actor which coordinates a certain session between other actors, then this one dictates the order in which things happen.